We'll discuss about the binary eutectic alloy systems. I had already made a video on invariant reactions. If you have not seen the video yet, then go back and see the video first and then see this video. First of all, I will show you a eutectic reaction here. As you can see, the name of the reaction is eutectic. Its equation is this. The liquid is cooling and gets converted into the two separate phases of solid. So liquid is getting converted into solid, but not just one phase with two phases. So this type of reaction is called a eutectic reaction. Now in binary eutectic alloy systems, a very good example is of the lead and tin system. Lead and tin system. As you can see in this diagram, this is the composition line and this is the temperature line. And we can see that there are two different regions formed here. One is called alpha and another is beta. So this alpha is the region which is PB rich. As you can see that this is 100% lead and 0% tin. But this alpha region is lead rich and this beta region is tin rich. So these are two kinds of solids here. But these regions are formed due to the limited solubility, because the lead and tin have the limited amount of solid solubility in one another. As we go back again to the theory of it, you can see the author has written here that many binary alloy systems have components which have limited solid solubility in each other. The regions of restricted solid solubility at each end are designated as alpha and beta and are called the terminal solid solutions. So, and we call this lead tin alloy as eutectic alloy. Why we called it eutectic alloy? Because it melts easily. As you can see in the diagram here, in this phase diagram, that there's a dip at this point. The temperature has reduced, and we can also see that at this point the temperature is very low as compared to these points, where a liquid, if at the time of cooling, if it goes through this stage, that is at 55%, let's take it 55%, you'll see there is more temperature is required to change the liquid state. And at this point we can also see that there is another separate region. This alpha is liquid, this is pro-eutectic alpha. We call it pro-eutectic because it forms before the eutectic reaction, and this is not completely eutectic, so we call it pro-eutectic. There are different grain structures shown here by the author, that what type of shapes are formed during the reaction, and finally at the eutectic point a lamellar structure is formed. We will discuss it about later. But so eutectic is a Greek word which means that melts easily. So this alloy, lead tin alloy, melts easily because eutectic reaction takes place. At this point the melting point is very low, it is only 183 degrees centigrade, and when this temperature is reached and this concentration is reached 61.9% tin and the remaining is lead, then eutectic reaction takes place. But during the solidification, when it starts to slow down, it starts to cool down this alloy, because when we heat it up to, for example, 300 degree, it gets converted into a liquid state, the alloy. But when it starts to cool down and it reaches 183-degree temperature and the concentration of it becomes 61.9% lead, tin, 61.9% tin, and the rest becomes the concentration of the lead. So a point is reached at 183 degree when eutectic reaction takes place, in which the liquid gets converted into two separate phases of solid. It gets converted into the solid alloy, and it contains both the alpha phase and the beta phase, and this structure is formed. That is the lamellar structure. So this is the eutectic reaction.